Welcome to this explainer. Okay, so you mentioned that the pages in your physics textbook for Chapter 3 were a bit, well, completely out of order and honestly pretty overwhelming. And yeah, reading a jumbled PDF about abstract math, literally nobody's idea of a good time. So today, we're going to fix that. We are going to build your understanding of vectors entirely from the ground up, block by logical block. We're going to decode the jargon, put the pages in the right order, and make absolutely sure you truly grasp what this special mathematical language is all about. All right, let's dive right in.
Here's our roadmap to demystify Chapter 3. First, an intro to vectors and scalars. Second, breaking vectors into components. Third, unit vectors and addition. Fourth, multiplying with the dot product. And finally, fifth, multiplying with the cross product. We're moving strictly chronologically so you never feel lost. All right, Section 1, Intro to Vectors and Scalars. We're starting right at page 40 to define our very first building block.
So the physical world throws a whole lot of quantities at us. Some of them are super simple, like temperature or mass. If I say it's 70 degrees outside, well, you have all the information you need. That is a scalar. It has a magnitude or size, but no spatial direction whatsoever. But what if I tell you to move 5 blocks? You'd immediately ask, wait, which way? And that is exactly where vectors come in. The absolute crucial difference to remember here is that vectors require both a magnitude and a direction. Things like displacement and velocity, those are classic vectors. They don't just tell you how much, they tell you where.
Now, this illustrates our first major rule, adding these vectors together. Sand particle moves from point A to B, and then B to C. We can actually draw those movements as vectors. If we want to add vector A and vector B together to find the total overall displacement, we can draw them geometrically in what's called a head-to-tail arrangement. You literally just draw the tail of the second vector starting right from the arrowhead of the first. The straight line from the very start to the very end, that is your resultant vector. But let's be real here. Doing this on paper with rulers and protractors gets incredibly tedious really fast.
Which brings us to Section 2, breaking vectors into components. Since drawing is so tedious, let's jump to page 42 and make the math much easier.
This projection method completely solves our whole drawing problem. Basically, any two-dimensional vector can be broken down into pieces, which we call components. Imagine shining a flashlight from straight above the vector. Its shadow on the x-axis is its x component. Now shine a light from the side, and the shadow on the y-axis is its y component. By dropping perpendicular lines to the axes, we form a right triangle where the vector itself acts as the hypotenuse. We just use basic trigonometry here. The x component relies on cosine, and the y component relies on sine. It's actually pretty brilliant.
All right, time for your first check for understanding, pulled right from page 43 of your text. I want you to pause the explainer right now, take a close look at these options labeled A through F, and try to answer which one correctly shows the components forming the vector before we move on. Go ahead, hit pause and test yourself. Welcome back. Okay, so if you guessed the head-to-tail arrangements, specifically options C and F, you are absolutely spot on. Think about it. Vector components are really just vectors themselves, right? Therefore, they have to follow the exact same geometric addition rules we literally just talked about. The x and y components have to be placed head to tail to properly form the legs of that right triangle, making the original vector the hypotenuse. If you try to connect them tail to tail or head to head, it just flat out doesn't work.
Section 3, Unit Vectors and Addition. Now that we have our components, let's jump ahead to page 46 to introduce the mathematical language used to actually add them together algebraically. Unit vectors are such fascinating little tools. The unit vectors I, j, and k have a magnitude of exactly 1, and they completely lack dimension, so no meters, no seconds, just pure direction. Their sole purpose in life is just to point in a specific direction along our right-handed coordinate system. I points along the x-axis, j along the y-axis, and k along the z-axis. They basically act like little directional tags that we can attach to our scalar components. So instead of those messy, tedious drawings, adding vectors becomes a super simple 1, 2, 3 checklist. First, resolve each vector into its scalar components using sine and cosine. Second, group them up. Add the x components together and the y components together. And finally, recombine them to write the new vector sum. It's clean, it's algebraic, and it works every single time. Let's test that logic with another checkpoint from your text. Take a look at the orientation of vectors d1 and d2 here. I want you to pause the explainer again and figure out if their x and y components are positive or negative just based on where they point. Ready? Pause now. All right, let's see how you did. So vector d1 points into the upper right quadrant. Because it's moving to the right, its x component is positive. And because it's moving up, its y component is also positive. Simple enough. But look at d2. It points down and to the right. Moving to the right still gives us a positive x component, but moving down gives us a negative y component. Keeping track of these positive and negative signs is absolutely crucial when you're adding your components together. Moving right along to section 4, multiplying the dot product. Let's skip over to page 50 where things start to get a bit weird. In normal arithmetic, multiplication is pretty straightforward, right? But with vectors, there are entirely different ways to multiply based on what physical reality you're actually trying to describe. The first way is called the scalar product, or the dot product. This takes two vectors and produces a regular, everyday scalar number. The crucial formula you need here is a dot b equals the magnitude of a times the magnitude of b times the cosine of the angle between them. Let's see how this builds visually. The dot product is essentially multiplying the magnitude of one vector by the component of the second vector that runs along the exact same direction. It's really all about how much two vectors align. Notice that it relies on cosine. So what happens if the angle between the two vectors is exactly 90 degrees? Well, the cosine of 90 is 0. The component of one onto the other is 0, meaning if two vectors are completely perpendicular, their dot product completely vanishes to 0. Kind of wild, right? Which brings us to section 5, multiplying the cross product. This is on page 52, and it's our final block on vector multiplication. Okay, so what if we want to multiply two vectors and actually get a vector as a result? Unlike the dot product, the vector product, or cross product, creates a brand new vector. The magnitude of this new vector is found by multiplying the magnitudes of a and b times the sine of the angle between them. While the dot product was all about how much vectors align, the cross product maximizes when vectors are completely perpendicular. But remember, vectors need a direction, so where does this new vector point? Well, it always points perpendicular to the plane formed by the original two vectors. To find out exactly which way, we use a neat little trick called the right-hand rule. Seriously, do this with me right now. Hold your right hand up. Point your fingers in the direction of the first vector, vector A. Now curl your fingers naturally towards the second vector, vector B. Look at your thumb. Your outstretched thumb is currently pointing in the exact direction of the new cross-product vector. It's literally a physical rule you can take into any physics test. Time for our final interactive check right from page 52. Let's see if you can reverse engineer the formula. If vector C has a magnitude of 3 units and D has a magnitude of 4 units, what angle between them makes their cross product equal to absolutely 0? Pause the explainer, think about the formula we just covered, and I'll give you the answer in a second. Did you get it? The answer is 0 degrees or 180 degrees, because the cross product relies on the sine of the angle, and the sine of 0 is 0. Vectors that are perfectly parallel or perfectly opposite will always yield a cross product of 0. They have to have some perpendicular nature to cross with each other. Make sense? To summarize everything we've built today regarding multiplication, check out this comparison table. It perfectly captures the dichotomy here. The dot product gives you a scalar, it uses cosine, and the order doesn't matter. It's commutative. The cross product, on the other hand, gives you a vector, uses sine, requires the right-hand rule, and if you reverse the order of multiplication, your thumb flips upside down, meaning it is definitely not commutative. Your textbook actually drops this really great insight on page 50, reminding us that while vectors do borrow rules from ordinary arithmetic, they are a completely unique mathematical language. You can't just apply regular algebra blindly. You have to respect the geometry of the physical space they represent. We did it! We took those out-of-order, totally chaotic textbook pages and we rebuilt Chapter 3 logically, step by step. You now know what vectors are, how to break them apart, how to add them up, and how to multiply them into both scalars and brand new vectors. Now that we've decoded the jargon, take a look around you. The next time you walk down the street or watch a plane fly overhead, ask yourself, how might you describe that physical journey using only the language of vectors? Thanks for joining me on this explainer, and keep questioning the physics around you.